So good morning, everyone. Thanks for taking the time and joining us for the webinar series on MeshWorks version 8. This is the sixth webinar in the series where we are discussing various attributes of MeshWorks and how it is very useful for the CAE engineers looking to accelerate various aspects of the CAE process. So the earlier webinars had dealt with sheet metal modeling and how MeshWorks makes a difference there. We had also worked on plastic parts modeling and how MeshWorks adds its value. Besides that, we have also looked at the feature-based tetrameshing as well as the hexameshing. Besides that, we have looked at various model assembly tools in MeshWorks. So all of these topics which we have discussed in the earlier sessions now are available as videos in the DEP USA website. At the end of this session, when you receive a note, you will also see a link where you can go ahead and review these older webinars if you didn't get a chance to attend them earlier. So with that, we would move into this session as part of continuation of discussing various features of MeshWorks V8. In this session, we are continuing to go ahead and look at how MeshWorks is able to add transformation as a pre and post processor. This time we are going to focus on two important pillars of MeshWorks version 8. One is the integrated modeler and another one is the associative modeler. Besides this, the other two pillars are the automated modeler and the parametric modeler. So they are the other two pillars. So this session we are going to look at integrated modeler and associative modeler. Now going into the next slide where we give an overview for those who have attended MeshWorks this series for the first time. MeshWorks is a CAE platform, a flagship CAE platform of Detroit Engineered Products, and the intent of the CAE platform is to act as a pre and post processor for various finite element / CFD activities that happen across industry verticals, be it automotive, be it aerospace, heavy engineering, biomedical, energy, or the transportation segment like shipping. So that being said, is MeshWorks a newer platform that has come up now? The answer is that MeshWorks has been a leader in the area of morphing and parameterization of finite element and CFD models since a long time. And it had an excellent interface with several optimizers, letting the CAE users optimize the performance driven by finite element models. Now we have added the geometry cleanup engine. Besides that, we have also added up the meshing engine, then the model checking as well as the post-processing modules, process automation modules that have been added up, and now as MeshWorks version 8, it's a completely integrated CAE platform. So that's the brief history of what MeshWorks was and what MeshWorks is today. And this pie chart is fairly representative of it, as to we would like to get your focus on to see these 5 important segments where MeshWorks plays a role irrespective of industry verticals. MeshWorks plays a role as a pre and post processor, be it sheet metal casting or plastic parts or non-metallic foam kind of parts. MeshWorks is always there as a pre and post. Besides that, MeshWorks also plays a role as a morphing and a parameterization engine. It has interface to design optimization tools. So that sort of gives you a complete breadth in terms of model building and optimization ability. Now, just to give you an overview as to what the MeshWorks' end-to-end feature is, the idea is to generate a solver-ready model from MeshWorks from the pre-processing side. And as you can see here, in an automotive context, you are able to see MeshWorks handling plastic parts as well as the complete subassembly including the model assembly tools, and then the complete vehicle level sort of assembly tools. It is able to build up the complete powertrain assemblies, as you can see, besides the plastic parts and sheet metal parts. So it is sort of is a complete full-fledged modeling tool, and it develops the full models, system level models for LS Dyna and Astran Simulia, those kind of solutions. That's something that's very important that we wanted to bring up to you. Besides that, now I would like to take your attention to the key differentiators of MeshWorks. We typically identify as the 4 pillars of MeshWorks product version 8. So one important pillar of differentiator is the integrated modeler, which we are going to see now as to how it helps the CAE engineer save time. We are also going to see associative modeler today and what is its impact in terms of helping CAE engineers save time. Besides that, in the next set of webinars, we are also going to see what is the use of parametric modeler and what is the benefit of it besides the automated modeler, where we are able to automate CAE processes without having to master a programming language and without having to write lines of code. So it's more a GUI driven automation development process. So these are all the 4 important ideas from MeshWorks version 8 that we would like to bring to your attention. In this session, I'm joined by my colleagues Gautaman and Bharat. They are going to share with you and demonstrate live various aspects of integrated modeling tools in MeshWorks, where you can start off with a single CAD database and end up with more than one solver attribute model. Maybe start off with a CAD database and end up with an NVH and durability powertrain model, or start off with a CAD database of sheet metal assembly and end up with a crash model and an NVH model, not just the nodes and elements but with connections. So that's what they're going to take up and share with you some of the tool sets from integrated modeler. And also on the associative modeler, they're also going to demonstrate how the existing mesh can be updated as we receive a new CAD automatically. How does the software understand the differences in between the existing mesh and the new CAD model and update itself? This takes care of the contacts as well. So those are some of the very important attributes that really solves the problem that as CAE engineers we face day to day. And now I would hand over the stage to Gautaman and Bharat so that they can walk you through certain demonstrations that can really illustrate the idea of integrated modeler as well as associative modeler. Over to you, Gautaman and Bharat. Thank you.
I'll directly move on to the demos. So the first demo that we are going to see is how integrated modeler is helpful in kind of a model conversion scenario. So here we have a very small assembly just to illustrate the demonstration with parts having a model assembled, machined and assembled as an abacus interface. As you can see, the mesh is fine and the bolts are being represented by solids with contacts, interface, etc. So now we can see how we can quickly generate an Astran model out of this particular scenario. So we can directly jump into the integrated modeler, and here we have the 3 options of generating a Dyna or an Astran or abacus. So I'm just going to use generate an Astran model. So we have 3 attribute files. So what you're seeing here is 3 columns, and we have a meshing attribute file, a modeling attribute file, and a solver attribute file. So the meshing attribute file is what defines the meshing conditions. So in this case, we are going to mesh the current part, the CAD part with a different template since we want to do an NVH meshing. So I'm just going to select the current part. In this case, it's just a mesh, and then the new part, which is a CAD data. And then I'm going to the new part type as CAD and apply a meshing condition. So I will just go to the file location and import the mesh template and say accept. So here the part gets displayed, and I'm just going to change the mesh type from a surface mesh to a tetra mesh. The same operation I'm going to do for the other part. So here I'm going to select an FE as the current part and a CAD as a new part, and then similarly apply a meshing template and say accept. So I'm just going to again modify the mesh type as the tetra meshing. Once the template has been set, we can just save it and do a return. And then now we have the modeling attribute file. So in this case, since we have only the bolt connections, I'm going to concentrate only on the bolt connection setup here. If you have a vehicle model, you can always modify it using the spot welds, adhesives, seams, etc., which I'll be showing in subsequent demos. So right now I'm going to the bolt connections. So here I have the bolt connector, which is go to the PAD and select the bolt connector. And then these are all the defaults where I would like to have my Nastran model built with RB2 beam and inter-rigids, and then I can directly go to the property. I will assign the properties of the particular beams and then the material of the beam. So I just say apply and return. So here I have now selected the machine modeling, and I'm just going to say generate a Nastran model. So as the Nastran model is generating, I would like to also let you know what is a solver attribute file. A solver attribute file is what is the type of element that we would like to convert. So by default, MeshWorks utilizes a mapping table, and the mapping table is actually customizable. If the user wants to customize any of the element conversions, he always has the freedom to customize it and save it in the solver attribute file. So in a moment, we can expect a model which has been converted with all the mesh and then the connections, the properties, etc. So this is actually a very powerful tool. So when we are trying to have an entire assembly of components, it takes only a couple of minutes to give all these inputs, and the rest the machine automatically takes care. So here, as you can see, the mesh is having a coarser mesh, and then the bolt solid connections has been converted into a 1D connections as per the Nastran template. So, and the materials, properties, everything has been converted into a Nastran format. So this is one scenario where we can use an integrated modeler. So integrated modeler can also be used as a part swap scenario, which is going to be our next demo. So here, any one of the attribute files can be used to generate any other model. So in the next example, so I have a diff case. So let me show you the baseline model, and then if I do a reverse, so we have the modified components where the mesh size is different, as well as some new features has been added, and some of the slots has been increased. So as you can see here, and now if I want to do a part swap scenario, the model that the baseline model is already a runnable model. So when we want to do a part swap, the model should also be a runnable model, meaning that the user should not do any kind of contacts updations, surface updations, etc. So if I am to look at this particular component, a single component, and say attached, you can very well see all the contacts and surfaces in the model. So now when we do a part swap with an even coarser mesh, so the contacts and surfaces, the bolts, everything should be updated automatically. So that is one scenario of the integrated modeler. So here, let me select all the models. and I directly go into the integrated modeler. And in this case, I'm going to generate again an abacus model. This is not a model conversion. It's a part swap scenario. So I'm only going to use a meshing attribute file. So here I'm going to choose my current part as the model with the fine mesh, and then the new part as a model with the coarser mesh. And in this case it's an FE part and there is no mesh template required, so I'll just say accept. And the mesh type is going to be tetra mesh here, and the same process I'm going to follow for the other components as well. So here we have a fine mesh as the current part, and the new part is going to be a coarse mesh, and it's again going to be an FE, accept, and the mesh type is going to be a tetra mesh. So that's all, it's been saved. So here I'm not going to worry about the modeling part, which is the bolt connections, and then again the solver attribute files. These are, I'm not going to worry, I'm just going to do a part swap scenario. So I'll just mention what is the new part and what is the old part, and just say generate an abacus model. So it identifies internally all the dependencies like the contacts, surfaces, element sets, node sets, which has been used for all our post processing, and then it updates automatically. So in this case, the model that the user is going to receive is a runnable model. So as you can see, the parts has been swapped, the bolt connections, everything stays, and the connector information has been updated. And if I am to only display the component that we previously saw and do an attached, so you can pretty much see that all the surfaces has been updated. It's the same surface, but it's been updated with the new elements. So there is no problem with the runnability of the model. So this is another scenario of the integrated modeler. And the next demo that we are going to see is how, again, the integrated modeler we have seen for the powertrain. So how is it going to use for our vehicle conversions? So in this case, I'm just going to show the conversion data alone. And again, I'm just going into the vehicle conversion, which typically uses the integrated modeler. So I'll just say identify spot welds. The tool automatically identifies the spot welds and highlights. So this is a dyna to nastran conversion. So let me just deselect this particular component and go to the next one and say identify adhesives. So if it is, I'll just select this one and let me go to the identify seam welds. So it identifies and then it highlights the seam welds, and if at all the user wants to modify any of the identification, he can always have the flexibility to add or remove. So in a moment we will see that the seam welds identification. So let me display the components, and now you can see that the seam welds has been identified and highlighted. And now the third one is identify the rigid patches. So it identifies all the rigid patches and highlights to the user. And the next one is going to be identify the CNRB elements. So all these are identified, and then once all this has been identified and set by the user just needs to do a convert crash to an NVH. So this typically takes like 2 or 3 minutes, and you can see that the process has been started. So in the interest of time, I've already have the output model. So here you can see this is the model that has been converted from an dyna to a nastran. So as you can see, all the spot welds, the seam welds, rigids, everything has been converted. And the tool is also intelligent enough to convert or create the bolts. So here it is a connection between two parts, so it creates the rigids and then connects with an interlinked beam. And also rigids which are not having the connectivity. So here we are just going to create a rigid patch And here, as you can see, the regions are created with one layer. And in the case of dependency issues, the tool automatically identifies that if it is going to connect, it's going to cause a dependency issue. And it just, in the local portion, it does not create that particular layer. So this is another scenario. The same integrated modeler can be used for vehicle side as well. And the next demo is going to be our associative modeler. So this is a very interesting part, and it can be used in a very daily scenario. So this is one model where we have received the, let's assume that we have received the model, we have meshed, we have done the text setup, etc. And now we receive the second iteration of the CAD data with very minimal changes. So in a current scenario, the engineer spends a lot of time in analyzing the changes, identifying the patches, locally modifying, recreating, and then again stitching back to the FE model, again does all the contact updations in those areas, etc. So what Associative Modeler does here is, once we mesh a CAD in MeshWorks, the associativity is built up. So user can directly use the Associative Modeler to do these kinds of tasks. So in this case, the tool only asks for very minimal inputs. So the source mesh data with CAD is going to be our the original mesh data where we have meshed it, and then the target or the modified CAD data is the second iteration of data where we have seen newly ribs has been added, some tubes have been created. So it's in a separate collector. And then it's just a kind of simple step-by-step proofreading. That is, we say identify changes. The tool looks for the changes in the CAD, identifies and shows to the user. And lets the user know these are the areas that is changed. And then once we say update CAD data with changes, it updates those changes to the original CAD. And let me do that. And once these changes has been updated, the user can give a mesh template, and internally what happens is only those local regions are meshed with a mesh template. It need not be the same template, it can also be a different template, and also make sure that the mesh is all stitched and the dependencies being updated. And dependencies meaning the element sets, node sets, surfaces, etc. So in a moment, we can see that the changes in a different collector. So as you can see, let me switch off the mesh now. So these are the regions that the tool has identified as changes. That is the gray color regions. As you can see, the ribs has been added here, and then some tubes has been drilled. So these are going to be the changes. And let me give a mesh template. And then say update FE model with changes. So this is a stage where it locally identifies, meshes the identified surfaces, and then stitches and updates the dependencies. So in a moment, we will see that also. So this is going to be a very useful tool, since the associative modeler is a scenario which is being used very frequently by almost all OEMs and customers. So now let me switch off the. So as you can see, the mesh wantedly given different element size on the fillets, and the meshing looks all well and good with all connected regions. And then if I am to switch on the surfaces, so even in all the changed surfaces, so this is typically a modified region or a changed region, the surface also gets updated. So this is one very good thing about the associative modeler. And the next one on the demos is the associative modeler being used in the CAD morphing scenario. So in this scenario of associative modeler, we have an original CAD data which has been meshed, and we receive a new CAD data, and we quickly update the new CAD. So now we have the in the second scenario of the associative modeler, we have the original FE model and the original CAD model, and then we use the FE model to optimize, and we get an optimized FE model. Now, how do we get this optimized CAD model? So here is one scenario. So we have the original baseline FE model, and we have done an optimization, and we have gotten all the changes on the ribs, etc. And now I'll show a scenario of how we can get this optimized CAD data. So this is our original FE model, and this is, by the way, the CAD morphing window that we are in. So here I'm just going to say this is my original CAD data, and the undeformed mesh is going to be the baseline mesh, and then the deformed mesh is going to be our optimized FE data, and I'll just say impose. So only with these three inputs, the tool automatically updates this original CAD data and gives the user an optimized CAD data, which can again quickly be used for all the designs and designs like the manufacturability, feasibility, etc. So the tool is currently now imposing the deformation, and maybe in just a couple of seconds, so the deformation has been completed. So as you can see now, this original CAD data has been deformed, and we now have the optimized CAD data. So the associative modeler is bidirectional. So these are the demos that we wanted to show you.
Thanks. Thank you very much, Gautaman, Bharat, for the demonstrations on integrated modeler and associative modeler. Before we open up the floor for questions, we thought we would summarize what we have observed and to recognize the advantages once again. So as my colleagues demonstrated the integrated modeler, we saw now how the situation has been really fairly better for the CAE users if they are working on some powertrain assemblies where they have the task of converting a detailed durability model to an NVH model, where the meshing attribute also undergoes a change and the way parts are connected undergoes a change. So in an essence, the integrated modeler has made that task easier if we look at it in the perspective of converting an existing model from one discipline to the other discipline. So that's the demonstration my colleague has taken up today. And he has also explained the applicability of the integrated modeler in a scenario where we have a body structure model built for as a master model built for crash, and we are intending to convert that model into NVH, and clearly illustrated how that entire process happens. It takes care of the weldings, and also it takes care of the connections, especially if there are bolted connections or if there are connections of a plastic part with an adjacent plastic part or a plastic part with an adjacent metallic part. So anything of that kind at either a body structure model level or the trim body level, those connections can be updated, and it's a great relief for the CAE user, as in terms of the time that it saves for the user, as the conversion is doesn't take too much time, and it also pays close attention to the various ways of connections and understands it and does the connection for you. So that's a good advantage that we could come across and inform you. And also, as my colleague presented, part swapping. This is also fairly a regular scenario that we see, where a particular part has been carried over from another program into this program, and we want to just update that part into this assembly. Now that has also been made easy with the integrated modeler, in the sense that it takes care of the connections also. So that's a good advantage that we would want to bring up to your attention. Besides that, the associative modeler is also very good. What we call it as is a bidirectional connectivity. Always we had a situation where there is a CAD data and a mesh data is built, and subsequently if there's a new CAD data, the mesh should automatically get updated. This is one important advantage of the associative modeler. The next level advantage of associative modeler is if I am starting to do changes with the FE mesh itself, and finally I want to update my CAD after making sure the performance is good, even that is possible. So if it is not that I can update my existing mesh to the new CAD, but also if I keep on making changes to the finite element model, I can also transfer those shape changes back into the baseline CAD data and get an updated CAD data. So that's a clear, complete bidirectional connectivity completed between CAD to FE and FE to CAD. That's an important thing. And you also observed that the connections are also very well taken care of. And in addition to that, the star surface definitions are also carried forward as we update the model, either from the perspective of integrated modeler or from the perspective of associated modeler. So these are few advantages that we wanted to bring up to your reference. And as always, the goal for us as the team which is working on MeshWorks is to bring in the drastic time reduction in the CAE modeling time to the users. That is absolutely one of our key goals. And the tools that we have built up, or we think that they are the steps in the right direction towards reducing the model building time. And we also want to make sure that there are opportunities where CAE has the ability to lead the design process. That is an important thing, I think, which got covered under the associative modeler, where we have made it bidirectional, where if the CAE has some ideas that it wants to implement in terms of performance improvement, so it can go ahead and implement it and then transfer those changes back to the CAD. So that is a clear advantage. And also we see this when we standardize the way we convert one model to another model, one disciplinary model to another model, in terms of identifying welding or gluing or bolting or riveting. If we clearly identify those connections and standardize them in a way we convert from one solver format to the other, that is a great way to minimize the error that we see in the manual process today, and also it makes it much more consistent. And these are some things that are very dear to us in the development of MeshWorks, and we want to stay focused on that, and that is what you see as a key value proposition slide as it goes up in your webinar session. And yeah, this is just a summary of associative modeler and integrated modeler for you. As a customer, what is the value that you can expect? As I summarized earlier, modeling time reduction is a very important thing that you will get as a benefit. And you are able to handle multiple discipline models based off a single CAD database, and also you have an option to update your mesh if the CAD gets updated. So these are pretty interesting things for powertrain users as well as the body structure users. And we see the customers whom we are talking to are really fascinated by the way that we are able to bring up the time reduction as far as the modeling time is concerned, and we are also making the conversion of models under the integrated modeler much more systematic, much more faster and better and more consistent. So that is a very important advantage that the customers recognize us for. And also the customers recognize us for our ability to complete the entire CAE workflow, where we start off from the CAD and go all the way through the model building process, solution process, and stay connected to the optimization process also. And finally, after you optimize, we always transfer the information back into the CAD so that you complete the entire loop. So many of the prospects and customers do appreciate that. These are some of the thoughts that we wanted to share with you in this webinar. Before we really thank you very much for your time, and now I think we are open for questions, if any. Thank you. So always users ask us if these tools, as we demonstrated, predominantly the tools were having powertrain assembly or a vehicle assembly. They look like an automotive centric. Can we have a durability model or an Astran model from an heavy engineering application? Will it work the same way, considering the welding processes are different and all that? Our answer is yes. The more or less the tools are robust enough to expand itself to the other disciplines, and it is equally applicable there. And the other aspect that we get to here is if I have a skin mesh model for the CFD, and if there's a new CAD coming in, now I want to update my skin mesh to the new CAD pretty quickly and get going without I having to really spend too much time in organizing the data and then generating the grid. Yeah, this is pretty much applicable. The associative modeler is not just a durability modeling a tool, but it can also stretch itself to whichever model